Hi, my name is Brian Caffo. I'm in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health, and this is a lecture on expected values in the statistical inference class in the Coursera Data Science series. This class and series is co-taught by my collaborators Jeff Leake and Roger Peng, who are also in the Department of Biostatistics. So we're going to talk this lecture about expectations. And this is a different thing than the kind of vernacular expectations. So it's not like when, say, my bosses tell me, Brian, we expect you to behave more professionally. It's not used in the same term, in the same way. So the expected value here, well, I guess in a little bit of sense, they're talking about we expect you to behave relative to norms, right? And here, the expected value is kind of the norm or a typical value of the random variable, or the most typical value. So more exactly, the expected value is the mean, so-called mean of a random variable, is the center of its distribution. It's the sort of one way we could define center. So for a discrete random variable x with a probability mass function p of x, it's defined as follows. Just the sum x p of x. And we write expected value of x like that. And I don't know why, but we statisticians like to put brackets around the expected value instead of curly braces. So I don't know why, but to me, that is like nails on a chalkboard. So I'm going to scratch it out because it looks so bad. So at any rate, that's what we do. Okay, where this sum is taken over all possible values of x. So the idea of expected value is it borrows from the physics definition of center of mass of the collection of locations and weights x and p of x. So if you have a collection of weights like this, and here's x as your locations, and these things all weigh relative to their height, if you could try and figure out a place to kind of put a fulcrum to balance this out, that would be the center of mass, and that would be the expected value. So here's an example that we'll use kind of throughout the two classes, that the inference and the regression class, where in the using our package, there's this data Galton, and it has child and parents' heights. And so, imagine trying to, again, put the fulcrum point in a place that balances out these things as centers of mass. And it's interesting to note that if these are the population probabilities, these heights are the population probabilities, then you get the theoretical or exact mean. And if these guys are the empirical probabilities, then you get exactly the sample mean. So it's interesting to note that the sample mean and the population mean can be viewed as being calculated the same way as trying to find the point on the histogram that balances them out. And let's actually do this experiment with manipulate. Okay, so here's my code. I'm going to do library manipulate, and then I'm going to create my histogram. And then here's my slider right here. And so I can move my slider along, and it will give me my measure of imbalance, and I want to minimize that. So it's saying what mu is it at, and where is my measure of imbalance at? Well, 67.5 seems pretty good. Oh, even better. Oh, there we went up. So it looks like somewhere around 68 is what the mean is going to be. Now the slider is not perfect, so you have to do this numerically, but this can show you, as you you're digitally moving this red bar, basically the fulcrum point around, and this imbalance is telling you how kind of much this would teeter or totter as you did it. Okay, and I give you the code right here, and then here's kind of the output with the actual mean. In this case, the mean is the function mean just gives you the empirical mean of this process. So, but again, here I'm doing it the empirical mean of some empirical data. If these were the true population proportions, then this would be the theoretical mean. Here's another example. Suppose we flip a coin, and it's declared 0 or 1 corresponding to head or tail respectively. what's the expected value of x? Well, if we do our calculation, it's 0.5 times 0 plus 0.5 times 1, or 0.5. But it's obvious if you think about this geometrically. We have two bars, one at 0 and one at 1. If we want to balance that out, we got to put something right there at 0.5. Okay. Again, same idea. We know that if we have a die, we have a bunch of bars, 1, 2, 3, 4, 5, 6 at 1, 2, 3, 4, 5, 6. We know that the center of mass has got to be right in the middle at 3.5. Well, let's do it, right? It's 1 times 1, 6 plus 2 times 1, 6 plus 3 times 1, 6 plus 4 times 1, 6, 5, 1, 6, equals 3.5. Okay? And let's see. There we go. Okay, so it mirrors exactly what we would know would happen. For a continuous random variable, it's the same thing. It's just maybe if instead of it having little bars, if you had like maybe a piece of wood or something that you cut out in exactly the shape of the density, and you wanted to balance it out, right? So it works out that this expected value of x is the area under the function t times f of t, or where t is a dummy variable here, the u times f of u or whatever, and this is just the center of mass for a continuous body. Okay, easy enough. So consider a density that looks like a brick. Here's an easy one for us. So the density looks like this guy right here. Looks like a brick. 0, 1, height 1, which is a valid density, right? It's bigger than 0 everywhere that it's positive, or everywhere that it's not exactly 0, it's bigger than 0. And its total area is area of the base times the area of the length of the base times the length of the heights, which is 1 times 1, or 1. So it's a valid density. Then the function t times f of t, right, just looks like this triangle, which is actually the density we had from before, but we're not thinking of it that way. We're thinking of this as t times f of t. And so if we had to integrate this guy, right, we know that's 1/2 the area of the base, which is 0.5, times the height, which is 1, which is 0.5. Okay, but we also know, just looking at this brick, if we had to balance this mass out, we would just put our finger or whatever right there at 0.5. We knew geometrically what the answer is, but it's nice that the area calculation also works as well, the definition. So expected values have some rules that are very convenient. It's a linear operator, so if a is not random and b is not random, then the expected value of ax plus b is a expected value of x plus b. Expected value of x plus y is expected value of x plus expected value of y. So for anything linear, expected value works great, but you can't, it doesn't work always, right? So expected value of x times y is not expected value of x times the expected value of y. It's not. No. Okay. And then expected value of, say, for example, x squared is not, in general, equal to the expected value of x quantity squared. Okay, so keep that in mind. But for linear things, it works great. So we can calculate things that you wouldn't think seems like they would be hard to calculate. Suppose we flip a coin x and we simulate a random uniform number. So a uniform number is that density that looks like a box, y. And so they both had expected value of 0.5. What's the expected value of their sum? Well, that's a hard random variable to talk about because it's neither discrete nor continuous, right? It's got this weird bump in the instances where x has a 1, where x takes on value exactly 1. So it's a weird random variable. It'll be kind of hard to work with. On the other hand, we can calculate the expected value very easily. It's the expected value of x plus the expected value of y. 0.5 plus 0.5 equals 1. So what this would mean is if you were to simulate a lot of coin flips and add to them a bunch of simulated random uniforms, add them together, and then take the average, but do it thousands of times. Really take the average of thousands and thousands of instances of a coin in a random uniform, then that would limit to 1. So another example is you roll a die twice. What's the expected value of their average? Well, one way to do that would be to roll the pair of dice over and over and over again. Every time you got 2 dice, you get an average. You would use that and you would do it enough so you know pretty much exactly what the distribution of the average of 2 dice is, what the mass function was, and then calculate the mean of that distribution. Another way to do it would be to note that the two dice, if we considered them ordered, maybe one was red and the other was green, and you wrote the red one out first and the green one out second, they can only take 36 possible values. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 6, 2, 1, and so on. Each of those combinations of values has probability 1/36. Each of them has an associated average. You could collapse the averages and figure out exactly the probability distribution for the averages. Then from that probability distribution, you could figure out its mean. You don't have to do any of that because we know that the mean, you don't have to do any of that because we know that if we just take x1 plus x2 over 2, where x1 is the first die roll and x2 is the second die roll, and we just distribute our expected value and pull the half out, we get 1/2 3.5 plus 3.5, which is 3.5. Isn't that interesting? The mean of the average of two independent die rolls is exactly the mean of an individual die roll. Interesting. That's foreshadowing because we're going to talk about that more. I hope the appropriate dramatic tension was built up after I said that. So the point I would like to make is, so we just described how you do that for two dice, but you could do it for three dice. You could take the average of three dice. So you could figure out 6 cubed combinations. Each one of them yields an average. They have probability 1 over, the combinations have probability 1 over 6 cubed, and there's duplicates of the average there. So if you were to collapse and figure out all the different possible values of the average and how many times they occur and figure out the probability associated with it, you get a probability distribution. That probability distribution would have would have a minimum, right? The smallest value the average could take is if you got 3 1s, which would yield an average of 1. The largest it could take is if you got 3 6s, that would yield an average of 6. So anyway, that distribution has a mean, right? And that mean works out to be 3.5. And so we don't have to go through that whole process. And what it boils down to is this following statement. If we have a bunch of random variables, they don't have to be independent even, and each of them come from a distribution with mean mu, then we can calculate the expected value of their average, right? So their average is the sum times 1 over n, but 1 over n pulls out, the sum pulls out, and we get the average of the individual random variables. Each of that's mu. Mu added up n times is n mu, but we're dividing by n out here, so it winds up to be mu. So the point being is if you have, you don't have to figure out this complicated distribution of the average in order to figure out what the mean of the average is. We just know it. So that's interesting. And this property, and it's also, it also shows that the sample average, right? The sample average is the expected value of the sample average is the population mean that it's trying to estimate. And then so it's a good estimator in at least that sense. So when the expected value of an estimator is what it's trying to estimate, we say that the estimator is so-called unbiased. In other words, the distribution of the statistic, which, right, the individual observation comprising a sample mean are random, so the sample mean itself is a random, so it has a distribution. The distribution of that statistic is centered exactly at the spot that you'd like to estimate. The benefit of using the sample mean, say instead of an individual data point, which is also an unbiased estimate, is that the sample mean we'll see is more concentrated around the population mean. So it's a better estimate. So that was more foreshadowing to talk about our favorite measure of spread, which is not the amount of peanut butter left in the jar. It is in fact the variance. So the variance is, as we mentioned, a measure of spread. It's defined as follows. If x is a random variable with mean mu, then the variance of x is defined as expected value of x minus mu quantity squared. Right? So notice this square is inside the expectation. We just write var x. And for some reason, we don't seem to mind parentheses for variance. While expected values, we like brackets. Don't know why, but we do. I think it's maybe historical reasons. So the expected value is the squared distance from is the expected squared distance from the mean. That kind of makes sense, right? If you have a if you have a distribution and you have its mean, right? Sort of like taking every point and taking its squared distance and a distribution that looks like that, the points are on average going to be more distant from the mean than in a distribution that looks like that. Okay, there's a convenient computational form for the variance, which is that it, instead of having to actually subtract the mean off from every point and then square and then multiply it times the mass function or the density function and sum them up or integrate, we can actually just take expected value of x squared and subtract from it mu squared, where this guy, this thing here, even though we're subtracting, is guaranteed to be positive. I always get this question every year, and so let me see if I can do it justice without confusing everyone. So let's take a discrete random variable. I want to calculate expected value of x squared, right? You can think of, like, let's suppose I want to calculate the expected value of the square of a die roll, right? I could just, if p of x is my mass function, I could just calculate that summation right there, where let me write px of x, where that's the probability associated with x, and then I just multiply it by a square out front. Or I could calculate expected value of y equal to summation x y p y of x, where py is the probabilities associated with the squared values of x. In this case, x can take, p of x. X can take value 1, 2, 3, 4, 5, 6. For my die roll, p of x is 1/6, 1/6, 1/6, 1/6, 1/6, and 1/6. And then here my y can take values 1, 4, 9, 16, 25, and 36. The probability is 1/6, 1/6, 1/6, and so on. So this is py of y. Sorry, it should have been a y right there. This is px of x. And the point being that these two things are equal. And I think it's pretty clear. You can see if I multiply these guys times 1/6, these guys squared times 1/6, I'm going to get the same answer as if I multiply these times the collection of 1/6 and add them up. The point is that you don't have to figure out what's the distribution of the random variable represented by x squared, then calculate its expected value of that mass function. You can just put the x squared in front of the mass function for x, and it works out to be the same thing. And the same is true for continuous densities if you're working with the integrals. Okay. The other nice thing about a variance that we know about variances is that if you pull a constant out of a variance, it gets squared. And then the square root of a variance is called its standard deviation. So, we might write standard deviation x. But notice this property, by the way, says that if you pull a constant out of the standard deviation calculation, standard deviation of ax is equal to a standard deviation of x. So it's squared if you pull it out of the variance, and it's back, a just gets pulled out of the standard deviation. And I like standard deviations better than variances because they're in the same units as x. All right, let's go through a conceptual example. What's the sample variance from the result from a toss of a die? So recall the expected value was 3.5, and then expected value of x squared, here's this guy, works out to be 15.7. Our variance works out to be around 2.92. So variances are a little bit harder to interpret than means, but fortunately, Chebyshev, a Russian probabilist, came up with a nice interpretation. The probability that a random variable is more than k standard deviations from its mean turns out to be less than or equal to 1 over k squared for all distributions, discrete or continuous, regardless of anything else about them. So what this means is the probability that a random variable lies more than 2 standard deviations away from its mean is 25% or less. 3 standard deviations away from its mean is 11% or less, and 4 standard deviations away from its mean is 6% or less. This is a bound. It might be a lot smaller. We know for a normal, for example, 3 standard deviations is way out in its tails, and that it's only 1% of being that far or further away. But these are benchmarks for interpreting variances. So let's say IQs, let's go through an example. IQs are often said to be normally distributed with a mean of 100 and a standard deviation of 15. What's the probability of a randomly drawn person having an IQ higher than 160 or below 40? Well, that's 4 standard deviations away from the mean. So Chebyshev's inequality says that this probability should be no larger than 6%. But it's probably a lot lower than that, but certainly no larger than 6%. So in fact, IQs are often thought of as being bell-shaped, in which case this is very conservative. If, by my calculations, it's 10 to the minus 5th, not 6%. That's 1,000th of 1%. Okay, so a former buzz phrase in quality control, industrial quality control, was Six Sigma, which I have to admit, I have no idea what Six Sigma really is from an industrial quality control standpoint. But I do know what 6 standard deviations away from the mean is. It is of the probability of a random variable being more than 6 standard deviations away from the mean is less than 1 over 6 squared, less than 3%. If it's a bell curve, then the event is on the order of 10 to the minus 9th. Okay, so that's interpreting variances. Variances are an important part of statistics, as are means. So both of those are so-called moments of the distribution. So what we talked about, so moments. And so what we talked about is the first 2 moments of a distribution, and they are certainly the most important ones. Next time we'll talk about how the variance does not add in the way that the mean adds. You can't just say variance of x plus y is always equal to variance x plus variance y. There's cases where you can do that and cases where you can't, and the standard deviation doesn't do that ever, because if the variance does it, then the standard deviation can't. So next time we'll talk about those kinds of rules for variances and how they relate to statistical independence.